time to get started. So today I'm going to try to finally get to talk about one of the things I tried to tantalize you in the first talk I gave, which is going to be about the quantum Hall effect. But before I start, I just want to point out some additional housekeeping. There is, of course, a luncheon the afternoon after my final lecture, which is December 10th. So as you came in, you probably saw there are actually two handouts, the one I wrote and the one that Beth wrote. If you'd like to attend the luncheon, just try to fill out that form and get it back to Beth by December 5th. If you want to just fill it out and give it to me after the lecture today, that's fine. I can collect them and make sure they get to her on Monday. But yeah, so it's the luncheon is December 10th after the last lecture. It'd be good to just have an RSVP in by the 5th so that they can make sure to actually order enough food for everyone so that it's not too disappointing. All right, so some of you may remember from my first lecture that I had this very funny plot of what happens. I take a material, I put it in a strong magnetic field, and I look at the resistivity, and the XY resistivity has these broad plateaus, and the normal resistivity is exactly zero at zero temperature. So what's the goal of this lecture is to just try to explain what's happening here. So before I start, I should kind of backtrack a great bit. So we're talking about looking at transporting charge in media. How do you move charge? You apply electric fields. So what are electric and magnetic fields? We all kind of have maybe a rough idea of it. But really all they are, electromagnetic fields, are vector fields in space, the idea being that it's something that exists everywhere. And everywhere in space, it's just an arrow pointing in a direction with some magnitude. So here is a picture of the electric field lines from an electron. An electron is negatively charged, so the field lines point towards it. Field lines kind of always are going to be pointing from positive to negative charge, or from, say, zero charge outside towards the small dot of negative charge that sits where the electron is. This is where I have shown you that these arrows have a magnitude, not just a direction. If I kind of scale them all to look the same, you can see that all of these arrows are pointing towards the center. So that's an electric field. You may be even more familiar with looking at magnetic field lines. So this is, of course, remember I told you last week that an electron is in fact just a tiny magnet. It's both electrically charged and it looks like a small magnet. And so here is the magnetic field lines from an electron, and you see that it really looks like the standard sort of magnetic field lines. I have arrows coming in towards the South Pole, pointing up towards the North Pole, and they kind of loop around on both sides. I assume everyone here is reasonably familiar with at least magnetic field lines, right? You can take little magnetic filaments, hold a magnet near them, and see them align. So how do we actually, if we really have a material, we want to put it in an electric field, how do we do that? You apply something called a gate voltage. So the idea here, this is a crude electrical diagram. I have a battery over here, plus on end one side, negative end on another, and I have a wire going to two metal plates. Because the fact that this battery wants to put a charge asymmetry, I find that at the negative end, I get a buildup of electrons on the edge of this metal plate. And at the other end, I have a buildup, well, a deficiency of electrons, sometimes called a buildup of holes. If I call something a hole when I'm talking about electronic structure, a hole just means that there was originally an electron there, and I took it out. So how I did this is here, I had a whole bunch of electrons here and a whole bunch of electrons here, but because I applied this battery, some of those electrons were driven by the battery to go around and build up on the other end. And now I have a bunch of negative charge here and positive charge here, and so the field lines are just pointing from negative to positive, pointing up in this direction. And so this is how you would actually just apply an electric field to a material. You just hook it up to a battery. And so I just want to emphasize this because it's very useful. Anytime, so this is kind of this direction is this direction here. Anytime I have a voltage difference, which is what the battery gives me, a voltage difference just automatically induces an electric field. So I'm going to use those two notions kind of interchangeably. I will either talk about voltage differences between these two sides and the electric field between them, and in some reasonably nice units, the strength of the electric field is just the voltage difference. So throughout this talk, I'm going to be talking about kind of voltage differences and applied electric fields interchangeably, and that's pretty much a safe thing to assume for everything that we're going to talk about. Again, with the caveat that I am not an electrical engineer, so if you are and you have a reason to explain to me why this is really wrong, it's an important way for computer science, I don't care, it doesn't matter to me. All right, so that's electric fields. How do you make magnetic fields? You may remember, you make magnetic fields by having loops of current. So if I have my wire here and I run a current through it, this is a little awkward picture, you get magnetic field lines that wind around the direction of the current, right? So if the current is going this way, there's circles of magnetic field lines around this wire all throughout. And so say I have my little 2D sample and I want to put it in a strong magnetic field, what I will usually do is just run a big wire around it, drive a whole bunch of current through it, and at least in the center, the magnetic field is pretty much pointing straight up. If I look all the way up here, this current will eventually wind around here, this field line will eventually wind around here, but in the middle of this current loop, the magnetic field is pretty much constant and pointing out of the plane of the loop. So these facts are the reasons that, motors work, for instance. Okay, so that's how you make electric and magnetic fields. What do they do? And again, this is probably familiar to at least some people in the audience. Well, we know that electric fields push charged particles, right? So you remember force is mass times acceleration. The force on a charged particle is just its charge times the electric field direction. So again, force is a direction, the electric field points in a direction. So if I have an electric field pointing to the right, electrons want to move to the left, protons want to move to the right. There's this technicality of a minus sign is just because we're almost always talking about electrons, not protons, and electrons have negative charge. So electric field points in one way, the electron wants to go the other way. And it's important to note that this accelerates the particle, right? It makes it go faster and faster and faster, which means that its kinetic energy is increasing. So when I put a particle in an electric field, it wants to add energy to the system, right? It's just dumping energy in. Which is very different from magnetic fields. So here, let me just explain this picture. These gray circles are supposed to indicate that I have a magnetic field pointing out of the screen. And this is a gun that shoots an electron, say, to the right. And there's this thing called the Lorentz force, and the Lorentz force points in a direction orthogonal to both the direction the electron is moving and the direction of the magnetic field. So the magnetic field is pointing out of the plane, the electron is trying to move to the right, so the force pushes it up, and it makes it arc in circles. Now, it's maybe not immediately obvious to this, but since the force is always acting in a direction that's orthogonal to the direction it's moving, it never actually speeds the particle up. It just changes the direction it's moving in. And it does not add energy. And what ends up happening is that if I shoot these electrons, they will just go in these large cyclotron orbits. So here at the top of the page is again this picture. I again have a magnetic field pointing out the plane. And if I have an electron, it'll move counterclockwise in cyclotron orbits. If I have a proton, it'll move clockwise in cyclotron orbits. Now, a reasonable question to ask is what happens if I apply both an electric and a magnetic field? And for what I'm interested in, I'm always going to have the electric and magnetic fields pointing in different directions, because that's what we're actually doing in our experiments that we're interested in. So that's this bottom line here. The bottom line is I have a magnetic field pointing, again, out of the screen towards you guys. I have an electric field pointing south. Now, the electric field pointing south tries to push the electron south, but then it feels the magnetic field, and it kind of gets stuck in these looping orbits. And similarly, for a proton, it gets stuck in these looping orbits. Now, you'll notice that the negative guys are looping down, the positive guys are looping up, but they're both moving in the same direction. Okay? And if you grind through the math, you find that these particles these looping orbits will slowly drift to the left, and the speed at which they drift is proportional to the strength of the electric field, and it's inversely proportional to the strength of the magnetic field. So I make the electric field stronger, they move faster. I make the magnetic field stronger, they move more slowly because these coils get tighter and tighter. I can kind of imagine decomposing this kind of telephone cord, which makes me sound very old, this telephone cord-like shape into basically, there's the orbiting cyclotron orbit piece of it, and then this constant drift velocity. And the frequency of this orbit doesn't depend on the electric field. It always is just linearly proportional to the magnetic field and inversely proportional to the mass of the particle. The drift velocity doesn't care about the mass or the charge of the particle. It just cares about the electric and magnetic fields. Are there any questions about this? Yeah.
So if in the electric field, if you're accelerating the particle, adding energy to the particle, kinetic energy, in order to conserve energy, where does that energy come?
That's a good question. So the electric field tries to add energy to it, but the force of the magnetic field pushes it away. So what's actually happening is that when it's moving against the electric field is taking energy away from it. When it's moving with the electric field, it's adding energy to it. So as I follow this, if I look very closely, it is speeding up and slowing down and speeding up and slowing down. But on average, the energy stays the same, right? If I go through one of these orbits, the energy here is the same as the energy here, right? The energy is decreasing because it's going against the electric field, and then increasing because it's going with the electric field, and then decreasing and increasing. So if I actually track the energy, the kinetic energy of the particle, it's just kind of going up and down. But if you averaged it, it would just be the kinetic energy of a particle with this velocity.
Okay, one other question on that. In the magnetic field, you said that the change of direction in a circular motion does not add energy to the particle, but I always understood any change of direction to be part of the definition of acceleration. If you make some, you have to.
I'm accelerating it. So if I just have a magnetic field, it is definitely true that I'm accelerating it. But as long as the acceleration is orthogonal to its current direction of motion, you're not actually changing the kinetic energy. That's clear because I know if I follow this, it's always going in a circle, and everywhere on the circle, its velocity is the same. Or sorry, the magnitude of the velocity is the same. The direction is different, but v squared here is the same as v squared here. Kinetic energy is just 1/2 mv squared. So when I'm in the cyclotron orbit, the energy of the particle is constant in that orbit. What's non-trivial, but you might worry about, is the angular momentum. But so I mean, the angular momentum is non-trivial because it is going in a circle, but I'm not concerned about that. Yeah.
On the previous slide. The one before that, I guess. Yeah, there you go.
Yep.
You have the coil at the bottom there. You said that it takes longer. It slows down as it goes up, and it speeds up as it comes down.
Yeah, you can just think of that as think of how the electric field acts on the particle, right? So here, let's think about a positive particle, so it wants to move in the direction of the electric field. So here, it's going up, and it's pushing against the electric field, so the electric field is pushing it backwards and slowing it down. And then once it finally turns around, now it's moving in the same direction of the electric field, so the electric field is speeding it up. But again, on average, those two things cancel out.
So it's spending more time to go up, and it's coming down faster, or vice versa.
Yeah.
So it's not a regular type of rotating like a wheel on a road. It's kind of a lopsided.
Yeah, I mean, yeah, it's certainly true that it's slower here than here, and in this case, it's slower here than here. But on average, it's a constant velocity. It's a constant velocity this way. It's clear that the up-down velocity averages to 0.
Yeah.
Right. So I can, on one time cycle, I can neglect it. Yeah.
Should the drift come out of the screen rather than being in the plane?
No. That's the interesting thing, is that the drift velocity is always in the direction orthogonal to the magnetic and electric fields. So there's only one direction left, right? The magnetic field is out of the plane, the electric field is down, so the drift has to be to the left. And the interesting thing I want to emphasize is that the direction of the drift does not depend on the charge of the particle, right? Both positive and negatively charged particles drift in the same direction.
One more question. So in the acceleration phase, let's say when you're going down, with the electric field, does that mean that in order to conserve energy in that phase only, I'm not talking about the overall average, but just in that phase, that something diminishes as the kinetic energy increases, meaning that would be the strength of the field? Does that?
Sure. So if you do this problem very carefully, and it doesn't actually matter for our purposes, but if you do this problem very carefully, when it's fighting against the electric field, it's slowing down, and that means it's actually dumping energy into the electric field. If I really built this in terms of, an array of positive and negatively charged particles on the two sides of it to give me this electric field, and when it's going down, it's taking energy back from that. If you did this very carefully, you could see that, okay, I have a bunch of charge pluses here and charge minuses here, and when it's going up, it of course pushes on them as well, and there's some energy exchange with them. But in the limit where I have a huge array of positive and negative particles, I just don't have to keep track of that.
Okay, I understand, but so what you're saying though is, just so in terms of what that means, that the field gets stronger or weaker, is that what it means?
The field changes. I don't know exactly which sign it goes in either way, but it absolutely is the case that if I really built this out of a system where I really have charge pluses here and charge minuses down here, and I just ask where do they go, clearly the total energy is conserved, right? So if energy is leaving this point particle, it has to go into that array of charges that are moving it. But if I assume that those guys are very heavy, dumping energy into them doesn't move them very hard. Okay. So with this picture of this notion of kind of electronic drift, this is precisely the picture that I talked about in the first week, right? I have some thin slab that has a bunch of charge carriers in it. So in particular, the usual thing that's done in experiment is I have on the bottom half, say, gallium arsenide, and on the top half, I have aluminum gallium arsenide. When I put them next to each other, when you work out the details of what's happening in the metal, you find that, okay, so in the picture, this direction is the same as this direction. So in this little slab here, there are a bunch of free electrons that are not allowed to move up and down, but are allowed to move in the plane. Right? So this is what's called a two-dimensional electron gas. It, of course, isn't exactly perfectly two-dimensional, but if I imagine that this room in which they can move up and down is much, much smaller than these other extended dimensions, it's not too much of an approximation to say that these electrons are really basically confined to be stuck in a two-dimensional plane. Right? And so now, what we're interested in is just applying a magnetic field to be pointing out of that plane and ask what happens. And we know what happens, right? So if I just have these electrons, the magnetic field coming out of the plane, that these electrons will just go in little cyclotron orbits. I haven't drawn it there. It's not too important. And if I apply an electric field to the right, I know what happens, right? We just worked it out. We saw that they will drift in the only direction left that's different from the magnetic and electric fields, which is down. And if all of these electrons are moving down, that means that there's a net current, right? Because the net current is just a motion of charge. Of course, if I draw this more carefully, these aren't just moving in straight lines. They are moving in these drifting cyclotron orbits. But if you squint, you can ignore that structure. And if you just remember Ohm's law, the formula for the drift velocity and the fact that the applied electric field is just a voltage difference, and remember Ohm's law is I is V over R, or IR is V, it doesn't matter, then this Hall resistance, and I want to emphasize this is an XY because I'm looking at the difference between a voltage difference in the X direction and a current in the Y direction, right? Which is different than how we usually measure resistance, right? Usually resistance is I apply a voltage differential in one direction and I ask how much current is flowing in that direction. And that would be the normal resistance. Here I'm talking about something else. It's called the odd or Hall resistance. I'll usually call it either RXY or RH. And it's just this idea of I apply an electric field in the X direction, how much current is flowing in the Y direction. You go through this formula and you have this very simple, you get this very nice result. The important things to point out is that this resistance grows linearly with the strength of the magnetic field we apply, and it is inversely proportional to the number of electrons. So in fact, the more electrons we have, the less resistive the system is, or the more conductive it is, which makes sense, right? More electrons, easier to conduct. Conductance is just the inverse of resistance. It is worth pointing out here, I can write it down explicitly, that you'll notice that I applied an electric field in the X direction, but since these guys only drifted down, there's no current flow in the X direction. So the conductance in the X direction is in fact exactly 0. So if I think of this as a metal, it's in fact a perfect insulator. I apply an electric field in the x direction, and there is zero current flow in that direction. Now that's kind of in this impossibly pristine toy model of just electrons. And this is in fact exactly what's measured, right? You take your sample, you drive a voltage in this direction. Remember that driving a voltage is the same as applying an electric field. And I measure, say, current differentials, or this could be a driven current, and I measure voltage differentials, and you see how much am I pushing through here, and what's the voltage differences that I measure. And people measure this. This is now a plot of this line is that odd or Hall resistance, and this noise down here is the normal resistance. Magnetic field. You'll notice that weak magnetic fields, it looks pretty good. This looks pretty much like a straight line, which is what we expect, right? It's linear in the strength of the magnetic field for some particular sample. This is that particular gallium arsenide interface, so the details are important. You'll notice that the normal resistance isn't exactly zero. Now, remember, I had previously argued that it should be exactly zero, right? It should be exactly zero because these guys have to drift only down. But that's ignoring the idea that this isn't really a clean sample. There could be defects in here. These guys could bounce off those defects. And if they bounce off those defects or bounce off each other, they can have some weak net flow to the right as well. The details of that aren't too important. But that's the reason that this isn't exactly zero, right? So again, this works for weak fields, but it clearly does not work in strong fields, right? We've completely lost this picture of a nice straight line. But something funny is happening, right? I have these regions where, for wide ranges of the magnetic field strength, this Hall resistance is exactly constant and is not obviously related to the applied magnetic field. And the normal resistance is really sharply zero. So our picture was almost right in these plateaus in that the normal resistance is very zero, but this doesn't look like a straight line anymore. And we need to figure out what's going on here. Now, it turns out, if you look at this reasonably carefully, you notice that these are labeled by 2, 3, 4, etc., that you can actually fit the value of each of these plateaus with this very simple formula. You say the resistance is just, well, h over e squared. Those are fundamental constants that aren't terribly interesting. If you look at them in units, h over e squared is just 25 kiloohms, divided by n, where n is just an integer, either 1 or 2 or 3. So 1 is off this picture here, but here is 2, and you see that it is pretty much a good fit. 3, 4, these fits are extremely good to this formula. And so this is what we want to explain. Why do we have these very beautifully quantized results, and why do they exist for these wide regions? Now, of course, I spent many previous weeks harping about how important quantum mechanics is in electronic structure, and so no one should be surprised that, of course, the thing that we left out was quantum mechanics, and that's why this didn't work, right? So what do we actually need to do? You need to solve the mathematical problem of what happens to an electron when it's in a magnetic field in a two-dimensional sample. And so you open up your textbook and you get a bunch of ugly formulas. They're actually, if you're a mathematician, they're very pretty, but you know, they're not particularly pictorial. The things that I want to emphasize that come out of that mathematical calculation are the following results. First of all, you find that if I have a sample at some finite size, there's basically a whole bunch of energy levels at different energy values, and there's this fundamental length scale that comes out of looking at the quantum mechanics of this problem, which is pretty big compared to the microscopics, okay? So this is what's called the magnetic length, and if you want to work out what the units is, it's basically 25 nanometers times the square root of the value of the magnetic field in Tesla. Now, if we go back and look at some of our values for the magnetic field are kind of order 1 to 50-ish. So this number is going to be maybe 50 to 100 nanometers. And it's important to compare that to kind of the atomic size of the system. For that particular material I was looking at, gallium arsenide, the ionic spacing between the gallium and arsenide atoms is about half a nanometer. So this is much, much bigger than that. Right? So quantum mechanics in a magnetic field is blurred out. I don't have to worry about the details of this microscopic atomic lattice because of this quantum blurriness of the problem. This is different than the usual story of quantum blurriness where we say we can't know the position and the speed of a particle precisely. This is really blurriness due to the magnetic field being applied to the system. So these are pictures of the probability distributions for some generic wave functions. So there's this length scale and there's an energy scale. So what's actually happening is that quantum mechanically, the electrons are moving in cyclotron orbits whose radius is basically one magnetic length. But they're not just semi-classical movement, they're not just movements in these orbits. There's a kind of a hidden internal excitation degree of freedom that you can't see if you just look at the probability distribution of the wave function. And so the idea is that here I have a whole bunch of this is a crude picture of possible states the electron can be in, because I've divided my system up into chunks of magnetic length squared. And these have energies where n equals 0, so it's just 1/2 times this energy scale. If I look at these states, they are also states where each one takes up a space that's about 1 area of magnetic length squared, but they have much higher energy, right? Where this was 1/2 times this energy scale, this is 3/2, 5/2, 7/2, and so forth. And again, you can't just look at the probability distribution. You really have to look more carefully at the details of the quantum mechanics wave function, which is a little mathy and not important. The real punchline is this basic idea, okay? I have these levels, these energy levels that are really extremely degenerate. These energies are all pretty much exactly the same, and they have this wide spacing. So the energy difference between, say, any of these two states, even if the system is a little dirty, is negligible compared to this big energy difference between them. But I can crudely draw a picture where every state here corresponds to an electron in a cyclotron orbit. Now, because this is quantum mechanics, that means that if I have occupied all of these states and all of these states, I have these orbits for the n equals 0 level, and similarly, on top of them, those orbits for the n equals 1. And because of this hidden internal excitation degree of freedom, there isn't a Pauli exclusion principle telling me that those can't both be occupied at the same time. And so to kind of emphasize how tricky this is, here are two different states that have the same probability distribution for where the electron is, but they have manifestly different energies. So you really have to look a little bit more closely. What's actually happening in that case, if you want to get into it a little more carefully, is that the phase of the wave function is rotating clockwise by 2 pi for this state and counterclockwise by 2 pi for this state. And that's why they really look different, and they can be in the same spot at the same time. Like, this is really a technicality. I just want to emphasize this is the important picture here. For every one of these states, I can cut out a chunk of my sample with area magnetic length squared, and there's one electron that can fit there for each of these energy levels. All right? So then, this is our quantum mechanics problem, and then we say, well, actually, how many electrons do we have in the sample? And you just, remember, you always put electrons in the lowest energy state possible. So I first fill up this lowest Landau level, then I would fill up this next Landau level, so on and so forth. So here, this is a picture of saying, for instance, I filled up the lowest Landau level and the next Landau level, and then I've run out of electrons, there are no more to place. It turns out, if I want to ask, because of this one state per level for this area, if I ask what the electron density is, electron density is just the number of electrons divided by the area of the sample, it's going to be 2 times the strength of the magnetic field times this is for each individual level. So either this level or this level, it doesn't matter which one. The charge density in that particular level is going to be 2 times the strength of the magnetic field divided by the strength of the magnetic field of an electron. Because remember, an electron is itself a magnetic field. Don't worry about this. Don't worry too much about this factor of 2. It's not too important. The punchline at the end of the day is that if I fill up n levels, I have n times this unit of charge, amount of charge in my system. And then I can ask, how much does each one drift? So again, right, this is just the magnetic field from a single electron. It's not important. So, kind of doing this in a quasi-quantum mechanical way, we're going to assume that each electron drifts in that semi-classical way, even though some of them are on top of each other, and then we just go through the algebra, right? We write down Ohm's law, or we write down Ohm's law in terms of electric fields and local currents. You go through some algebra. You notice that, okay, this charge density was that charge density calculation we just did. This is the drift velocity. And at the end of the day, you reproduce precisely that result we had earlier, that this Hall resistance is this fundamental unit h over e squared, which is 25 kiloohms, divided by some integer n, which is just the number of levels we filled up. And this, in fact, explains precisely this value here, and this value here, and this value here, right? This is literally this number at 2, 3, 4, 5, and so on and so forth. So I want to emphasize that here I've been able to predict the value of the resistance in that plateau, but I haven't explained to you exactly why it's this wide plateau and not just a single point. The reason is the following. So let me just make a brief aside here. If I change the magnetic field, how strong it is, that clearly changes the magnetic length, and therefore it changes how many electrons fit in a level, right? Because the magnetic length went as the 1 over the square root of the magnetic field, and so, or sorry, when is the square root of the magnetic field in Tesla. And so, if I change that, I change how many electrons fit in each one of those energy bands, right? So that's this picture here where I have the number of states fitting in here scales with the magnetic field in each one of these levels. So let's imagine a system where I've tuned the magnetic field so I perfectly have enough electrons to fill up this level and this level. Well, this seems great, right? This seems like it has to give me exactly n equals 2. But what if I change the magnetic field a little bit, and I change it so that I remove some of these states by making each one of those electron orbits a little bigger, right? So I run out of room. Well, there were 2 electrons here. I have to put them somewhere, so I have to put them up in the next level. But that doesn't work, because this tells me that in this formula, n isn't just 2. I have to worry about these states as well, so it's really 2 plus this small excess up here, which tells me that if I change the magnetic field a little bit, the resistance should change a little bit. But that wasn't what we saw experimentally, right? Experimentally, we saw that you could change the magnetic field a little bit, and that value did not change. It was really strictly constant. So, do these electrons really have to get kicked up to this next level, or is there something else we can do? And so now we run into trouble because, you know, we tried to simplify the problem to make it easy to solve mathematically, and we made it too simple, and we ruined it. All right? So here's a plot of those nice plateaus fit with that straight line. Now, if I really did assume that every time I change the magnetic field from its dead center value, either at this level or this level or this level, if every time I did that, I had to move the electrons to that next level, assuming that the system is perfectly clean, and I do that calculation carefully, I would actually end up just reproducing that classical result we started with, which is that this has to be a straight line, which worked for weak fields, but broke down at large fields. I want to emphasize here that since I've drawn this line on top of it, I haven't drawn it perfectly. If I'd drawn it better, you'd see that it basically hits a piece of the middle of each one of these plateaus, and that's the point at which the magnetic field is precisely at the value that, even ignoring dirt and other effects, I would be sitting right at that value. But that's not what happens, right? We see that this red line, which is this Hall resistance, doesn't change as we move the magnetic field a little bit, and we need to understand why that's the case. And the reason that's the case is something called disorder. So of course, if I have a real sample, I have some piece of material I made in my lab, well, first of all, it's never even going to be a perfect crystal, right? It's going to be a little bit dirty. It might not be perfectly gallium arsenide. There might be some small amounts of other atoms. The atoms might be not quite out of position. And what that means is that the electrons don't just feel the applied magnetic and electric fields. Since this place that they're living is kind of bumpy, they also feel a potential valley, right? So this is kind of a contour map of the highs and lows of a particular material sample you're looking at, right? So blue are higher values and red are low. So I was just talking about classical electrons, and I had one here. It would kind of want to roll down to the bottom of this valley, roll down to the bottom of this valley. That's the idea, right? And the details of this aren't important, but it's very generic. Now, yeah.
The upper picture that you're showing there, is that essentially a two-dimensional one, or is Is it a projection of a three-dimensional one?
So this is there's a height, so okay. You can think of the dirt in this system as being the following. It's not an exactly flat two-dimensional system.
Okay.
These are peaks and valleys of that sample.
So it's a topograph.
It's a topographical map. Now, the system, of course, isn't bumpy in that sense, but you can model the dirt in the system as basically saying there are peaks and valleys, and if an electron is at a peak with nothing else done to it, it will want to roll down into the valley.
Okay.
And so these are equipotential lines, right? Now, something that isn't obvious, and I don't want to get into the weeds with the math of this, is that, of course, if I have a particle sitting at the top of a hill, it will want to roll down to the bottom, right? But if I have a particle sitting at the top at some point in here, and I also apply a magnetic field out of the board, you can grind through the calculations, and in the limit where that electron is very strong, well, if this picture wasn't here, these guys would all just want to go in nice cyclotron orbits, right? What happens when I have these when I have this topographical map is that electrons will really want to actually get stuck looping not on nice circles, but they'll get stuck looping on these equipotential lines, right? These lines of constant height of the hills. Okay. Now, if I have enough electrons to fill up the sample entirely, that's fine. But if I don't, that's not even that big of a deal, right? Because let's look at this very deep valley here. Imagine I have my magnetic field tuned just perfectly so that I have just enough electrons in the system to fill up every chunk of magnetic length squared of my sample, right? And then I want to change the magnetic field so I have one less electron. Well, I can do that by essentially removing, say, the electron that's sitting in the bottom of this valley here. Now, what was that electron doing? It was stuck sitting at the bottom of this potential valley. There's a hill here, so even if I apply an electric field, because it's stuck in this valley, it won't drift down. Because of the fact that there are these hills and valleys here. Now, what that means is that even if I remove, say, this one little electron here or this one little electron here, because those electrons were really trapped, they wouldn't have contributed to the net current flow down, right? It's only something that can really go all the way on some extended contour. Those are the guys that can contribute to the actual large-scale net current flow. So here's kind of a pictorial region, right? The idea is that I had my sample, and I changed the magnetic field. I made it a little bit bigger so that I had to remove one electron. And that just means that there's this little island in the middle of the sample where here there's kind of one electron per area, and here there are no electrons. But because it was stuck in this valley, like being stuck in this valley, it could not contribute to the net current flow. And so even though I'm not quite sitting at the precise value, the Hall resistance that I measure doesn't care about the effect of this electron, and it looks as if it had been a perfect sample at precisely the right magnetic field. Now similarly, let's say I change the magnetic field so that I can fit more electrons in. Well, the first place I can put a new electron in is going to be sitting in the next highest Landau level, but also trapped in some valley. And so even though it looks like I have to take an electron and put it into the next level, it's not in the next level in some extended state. It's also trapped in the sample, so this could be I equals 1, and this is, say, I equals 2. 2 electrons here, where there's only 1 electron here. But again, that additional electron is just stuck going in here. So if I think about the total integrated current, well, the total integrated current, it's moving in orbit, so it's going positively here, but negatively here. So again, the net contribution from these isolated electrons stuck in valleys of this topographical map do not contribute to the Hall conductance. Yeah, so this is roughly what I said, is this island. And the kind of crude takeaway of this is that what's really contributing, if I look anywhere in the interior, because this system is kind of dirty, right? It's not just that there's one valley and one hill. There are lots of these little circles. And so most of the electrons are really trapped on these circles, and it's only electrons near the edge that can kind of bounce off the edge as they try to follow these contour lines. Those are the only electrons that can contribute to net current flow. So pictorially, remember a few weeks ago we talked about pictures of densities of states, and so here's a picture of kind of the density of states before and after we make too many approximations. So here, if there's no magnetic field, there are no Landau levels, it's not interesting. Scattering is the same thing as disorder. Don't worry about that particular nomenclature. So again, if I didn't have any dirt, I would have these exactly degenerate flat energy bands where they're all of these states all at exactly this energy, and they're all very extended. They all contribute to current flow. But that's not actually what happens. Because of the dirt and the disorder in the system, these sharp peaks get broadened. And you see that most of these peaks are these kind of dotty regions, which is an artistic attempt to indicate that these are electrons that are really stuck going in circles on equipotential contours of valleys and can't give you net current flow. And it's only these special states, dead center, that are really extended, that live really at the edge of the sample, that can contribute to charge flow, right? So if I change the system so that I want to occupy some states in these localized states, it doesn't affect the Hall conductance, right? So this is what I'm going to say. So if I try to tune through this, you're going to find that it will not contribute to the Hall resistance. So what does this pictorially look like? Okay, so let's say we're sitting at some value of the magnetic field so that every state below this line that I've drawn here is a state that I want to occupy, right? Now, that's this value here. Now, look, there are a bunch of these localized states, but as we said, these localized states don't contribute to the net current flow. So let's decrease the magnetic field strength a little bit, and that makes us want to have to occupy more states. But I haven't hit any extended states, so this Hall resistance is still basically the same. But as I tune the magnetic field to be precisely at the value that I find new extended states, now this Hall resistance is starting to change. Because now I've introduced new states into the system that do allow for charge transport. So there are more things allowed to conduct. If there are more things that can conduct, the less resistive the sample is, so the resistance goes down, and then I pass through it, I'm on the other side, I have all of these extended states, and so I'm robustly in this plateau. Yes?
I was going to say, what is the purpose of that line with Fermi level?
The Fermi level is something you have to worry about if you're not working at fixed charge density, but you have a source or sink for extra electrons. It's not worth worrying about. The important thing is seeing that as I tune the magnetic field, I can go through including these extended states. So here, I have not included these extended states. These are the only extended states that can conduct, so I have a higher resistance. I tune my magnetic field until I allow for more extended states. I have more states that can conduct, so the system is a better conductor and thus a worse resistor, so the resistance goes down, and you just have to add up how many of these extended states we have.
So what is gamma?
Is the
Right there.
Extended, right.
Gamma is some notation from the textbook I stole this picture from.
Oh,
Don't worry about it. The important part of this picture is that if I look at what energies I have states and how those states behave, there are localized states that don't give net conductance, and there are these very special extended states that do give net conductance. And it's only when I add or subtract extended states that I change the Hall conductance. And that's the reason that I have this robust plateau. Right? So let me make one more emphasis. Right? So if I'm sitting here, it's clear that this system isn't going to be a good conductor for the following reason. Right? I've occupied all of these states. So if I want to add more current, if I want to get more normal current flow, I'd have to pop up an electron from here all the way into up here. That's a huge energy cost. So the DC normal conductance is 0. Whereas, if I'm sitting in the middle of this extended band, then it's very easy to just pop from an extended state below this line to an extended state above this line, and that's why this normal conductance is finite.
Now let me throw a rock into you. What happens when the temperature changes?
So this is all at essentially 0 temperature.
Oh, really? It is? Okay.
Yes, I should have made that more clear. This is all at effectively 0 temperature. These guys being 0, if I have something that's an insulator and I heat it up a little bit,
yes,
then those electrons that were trapped are allowed to jostle a little bit, and so it will conduct a small amount. And as I cool the system to 0 temperature, it really becomes a perfect insulator. So that's, yeah. I mean, of course, when you do these systems in a lab, you're working at probably microkelvins. But that's as good, that's close enough to zero temperature for what we're interested in. Are there any questions about this picture? This is kind of one of the key takeaways, this notion of the difference between localized and extended states. Yes?
This is the blue line represents.
Oh, the blue line is just saying that as I change the magnetic field, the how many states are in each of these places changes because the magnetic length changes. And so the idea is that as I decrease the magnetic field, I increase the number, I decrease how many states are in all of these regions. And so I increase how many of them I have to include to add up to the fixed total number of electrons in the sample. Any other questions? Great. So there's actually, there's kind of another toy model that's maybe a little bit, it's a better toy model than the model that we had from this perfect clean system that clearly didn't work, which is this picture of basically the system only being driven by edge states. The idea here is that the sample is so dirty that any electron that's really in the interior of this is always going to get trapped, going in an orbit in some potential valley. And remember, if it's a cyclotron orbit on flat plane, the electric field lets it drift, but if it's a cyclotron orbit trapped in a valley of some dirty potential, that valley stops it from drifting, right? So objects stuck, or the physics nomenclature is that they get localized. So electrons in the bulk are localized, they can't transport charge, and only electrons on the edge can transport charge. And the interesting thing is that they can only flow charge in one direction, which is not at all obvious. It's a consequence that you find. And the idea is that for every filled Landau level in that crude Landau level picture, there's one edge mode. So here is a picture where I basically have my sample, and if I didn't have to worry about the fact that there were edges, these bands would be flat in my Landau level picture, but there are edges because the electrons can't pop out. That means there's a wall here, which means that as my electrons approach the wall, their energy cross increases. And if I think of this in some being applied to some to some kind of, yeah. So if I ask about how many electrons they are, it's clear that if I want to fill up all of this one and all of this one, there's some max energy. So if I have in the bulk 2 Landau levels filled, at the south end there are these 2 light excitations, and at the north end there are also these 2 light excitations. And so that's this picture here. Is that for this filling up the first 2 Landau levels, on this edge, I have 2 electronic states that can only move left to right, and on the north end, I have 2 electronic states that can only move right to left. All right? So this is roughly a picture, but the idea is basically, if I really take seriously this issue of dirt in the sample trapping most of the electrons, what ends up happening is that, again, for every Landau level that I fill, there's one charge carrier at the edge, but it can only carry charge in one direction, which is very different than a normal wire. Yes?
When you talk about dirt, didn't the semiconductor have to be kind of doped originally? So is that included in these like dirty discontinuities?
Sure, good. So that's a good question. So of course, the fact that this is a semiconductor and not a metal is something where you have to. A semiconductor is a statement about what exactly the density of the states of the sample looks like, and you're absolutely right. I mean, we built, this is say built out of a particular gallium arsenide interface, so it's clear that it's 2 different materials sandwiched together to make something interesting. So that is in fact itself an inherent source of this dirt. Yes.
But now, have you seen in the lab where they just said we're not even going to use a semiconductor, we're going to actually use a pure piece of metal, or is it always? Seems like every paper I've seen, they've always kind of gone with a semiconductor, a fat structure or something.
I think.
I mean, maybe in your research they actually use a metal, but isn't it easier to get a semiconductor?
It's easier to take something that is a bulk semiconductor and have it look like a 2-dimensional electronic gas. But that's a question of kind of 3 versus 2-dimensional. Right? The idea being that if I didn't apply this magnetic field, I wouldn't have this level structure, and from a 2-dimensional point of view, it would look like a normal metal. But it's a semiconductor if I think about its behavior in that additional direction. Yeah. That is a good, important, subtle point for a lot of material sciences, but from a theoretical perspective, it shouldn't really matter. As long as you have a material that, from a two-dimensional point of view, looks like a dirty two-dimensional metal, you're fine. All right, so again, we say we have these edge carriers, and basically each one of these lines corresponds to one type of electron that can carry charge. So each one of these edge states can carry a current that's just going to be, well, E over H times the voltage differential between this end and this end. So you can kind of grind through some of the algebra. The point is that since the voltage only moves in this direction, now I'm driving a current through here to here, so I want the electrons to kind of align themselves so that these 1 and 3 and 3 and 4 and 4 and 2 are all at the same voltage, but because I'm explicitly driving a differential voltage between this end and this end, there's a machine in between here driving this current, which tells me that the voltage here can't actually be the same as here. But the voltage all along these lines is the same because I have these charge carriers carrying it along. And similarly for the top half, I have these charge carriers carrying it along the whole way, except for the fact that I have a machine stuck in here driving a voltage. So you have all of these voltage differentials that are the same. And you remember we had that formula for what the current of each band is. So if I have n edge states carrying charge, you just work out Ohm's law and you find that this whole resistance goes as 1 over n. And the only thing we've assumed here is that we're not in the middle of an extended band. So I only have these edge localized charge carriers. So from this edge point of view, you can kind of perfectly predict that these plateaus exist, and they should be reasonably robust, as long as we aren't happening to be in this awkward middle area where this idea of just charge carriers on the edge really breaks down. Are there any questions about this? No, good. All right. So the question is this the end of the story, right? I've given you a somewhat crude but reasonably self-consistent mathematical story for why, when I make this magnetic field be really strong, there are wide regions of magnetic field strength where this Hall resistance is exactly flat, why the normal resistance is exactly 0. This might sound a little confusing, right? Because I kept telling you it was an insulator. It turns out that if you go through things carefully, when the Hall resistance is non-zero, you can think of this as actually just the conductance. I can explain that in a little more detail if someone's interested, but you should really think of this as a plot of the resistance, and this is a plot of the normal conductance. So in these regions here, it does not conduct charge normally. It can carry charge in a direction orthogonal to the applied electric field, but not in the same direction. And when I'm in these funny middle windows here, I find that it actually is a reasonable conductor, because I'm in the middle of a conduction band. And that's this punchline here. But so again, is that the end of the story, right? There's some simple story. All I had to do was think about kind of very weakly interacting electrons and some material, and I explained all of this. And I like to think I at least gave you a picture of why, for every field Landau level, there's one edge state, and if I just add up the contribution of each one of those edge states, I get exactly that quantized result. But of course, that isn't the end of the story, because those are only the integer Hall plateaus, which were the first ones discovered, and some of the nicest ones. So here's some, unfortunately, very blurry-looking experimental data, where here, the important thing to look at is the numbers labeling each one of these little windows here. So here's 1. That's the n equals 1 integer Hall plateau. Here's 2, 3, 4, so on and so forth. But it turns out that the first non-trivial one discovered is that when you crank up the magnetic field really high, you find one where this Hall resistance isn't just 1 over 1 or 1 over 2. It's 1 over 1/3, which is very puzzling, right? And there are other ones, 2/3, or sorry, 2/5, 2/3, 4/9, all of these funny fractional values. And remember, if there's a fractional value, that means that in our Landau level picture, we're really not anywhere near being in the middle of a sample, right? If you're at 1/3, that really pictorially means that you are in a state that looks much more like this than in between. Now, this is of course a crude mock-up. What it really would look like is being halfway in the middle of this line down below. But the important thing is that from our previous intuition, the location where these plateaus like 1/3 or 3/7 are appearing are places where our previous calculations told us, no, this should be a simple, normal conductor. There is no robust plateau. So what is happening here? And the answer, this is what I'm going to try to talk about next week, is that when you have these non-trivial fractional fillings, the idea is that you have a whole bunch of electrons. And what was the one thing that we ignored when we went through the details of the calculation, right? We talked about how the electrons feel dirt, but we never talked about how the electrons bump into each other, right? Electrons are, of course, charged, and so two electrons should repel. And we basically ignored that for the entirety of this calculation. And the answer is that you can't ignore it for all of these other non-trivial states. And that makes the problem, on the one hand, a harder math problem. We have to solve a bunch of interacting quantum mechanical objects bouncing around on top of each other. On the other hand, it provides us with much more interesting features, right? It's only in these fractional plateaus that you get what I talked about in the first week, these anionic particles, particles that are not bosons or fermions, but have fractional statistics. And you also get particles that have fractional charge, which sounds very confusing, right? I have a system, it's made up of a bunch of nuclei and electrons, but when I look at it carefully, I find that there are excitations of the system that do not have, say, the charge of 1 electron or 2 electrons. You get things that have the charge of 1/3 of an electron, or 1/5 of an electron, or 1/7 of an electron. And it has to do with just properly treating this non-trivial interacting electronic system. And that's what I'm going to talk about next week. Thank you. Questions?
When you run the experiment, I know you said you were like...
I don't run experiments. I want to...
Okay, when the experiments are run,
Yes.
you said they were, not absolute zero, but pretty close to zero. Is there heat change? Is there delta change of heat? In other words, as this happens, is there an expression of heat?
No. So,
Okay,
sorry, let
even
me...
with the-
When I'm in one of these thick plateaus, if I'm in one of these plateaus here,
Yeah.
roughly speaking, the fact that the normal conductivity is 0 tells me that I don't have to worry about heat effects. If the system is very cold, the idea is that there are two energy scales. There's the energy scale of the temperature that you're looking at, and there's what's called the energy gap, which in the integer state would have to do with, let me find the picture. So there's also this thing called the energy gap. So this is a plot of energy. And so, again, if I'm interested in things like large-scale transport, localized electrons, just like they can't, when it's stuck in a point, it can't carry charge, it obviously also can't carry energy. So if I wanted to transport energy, I'd have to look at the energy scale that goes from taking an electron here and knocking it up here, or here and knocking it up here. And so if that energy scale is much, much bigger than the temperature scale at which you're looking at the system, which in all of these cases it is, then you can basically completely ignore heat transport. And that's one of the reasons that it's fair to treat this system as essentially 0 temperature, which is not true when I'm in the middle here, right? Then the system can carry energy. Other questions?
I missed last week, but I watched the video and I have a question, if nothing else. So one of your slides last week, very early one, had the hot and the cold magnet. You were trying to show the arising, the magnetic field arising out of the spin of the electron. So you had, on the one side, you had the hot magnet where the alignment was chaotic,
Yep.
and so there was no overall effect. And on the cold magnet, you had the north and south poles aligned vertically and with larger distances between the vertical axes as opposed to. So that's the slide I'm talking about.
Yeah.
So I have two questions about that. One is, you're talking about each electron as having a definite spin state, where I always understood that in quantum mechanics, until you measure a spin state, a particular spin, it has no state. It's a superposition of all states. And secondly, the other
So
question...
let me answer that first question first. So no, the electron can, of course, be in a superposition of, say, spin up and spin down with arbitrary relative phases. That's a possibility. But once I prescribe the energy dynamics of the system, I can't have a system where the lowest energy state is that the electron is not in a superposition of up and down, but that the lowest energy state is that all of the spins are precisely aligned, so that if I measure any electron, I will always measure spin up at zero temperature. Of course, at finite temperature, there's always a little bit of thermal fluctuations that could happen. But I can set up a system where that if I had the magnet at strictly zero temperature, quantum mechanically, all of the spins are exactly aligned. And that was what was being done in that model, which is a special model.
So, are what you're saying that, I lost my train of thought. Are you saying that at zero, the actual, the quantum mechanical prediction is that there's a 100% probability of a particular spin? I'm
saying that in the limit, as I cool it to zero temperature. So
yeah.
I never have zero temperature in the lab, but there is a sense in which the colder I can make the sample, the less likely it is to measure one of the spins misaligned.
So basically, you're approaching 100% probability as you approach 0.
In this particular model of an infinitely sized magnet, where the magnet is the only thing in the universe, which is a toy model, then yes. But of course, that's not what, I mean, a real magnet does not look like that. In a real magnet, you do have to worry about how it interacts with other things. And so, of course, if I really tried to physically model an actual magnet in the lab, even as I cooled it to zero temperature, that probability would never be exactly 100% that it'd spin up, even in the limit as the temperature goes to zero. But that's, that's a technicality of finite size effects. But you're never actually going to measure it being pointed in the opposite direction if I make the system colder.
So the other question was, there seems to be, in that schematic, there seems to be a definite position to each electron in order to have this kind of spin. And
sure, so that was again another approximation where I said, I'm assuming that the atomic structure of my material is such that I can neglect the energy cost of wiggling the electron, because that's a much higher energy cost than just flipping the spin, right? Because it's always a question of the different scales of the problem, right? If the electron is stuck in some deep well, then the energy cost to move it even a little bit outside of that well could be much, much higher than the energy cost to just flip the spin. So if I want to add a little bit of thermal energy, it's always basically going to go into flipping the spin. Now, you of course are correct in saying that, technically speaking, if it really isn't an infinitely deep and infinitely sharp potential valley, there is a small probability that I'll measure it somewhere off-site, but you make approximations to make the calculation easy.
And this is also a result of bringing it down to zero or approaching zero. At other temperatures, you get problems with the location of the electron because it's a probability. It has no definite position until you measure. I guess what I'm saying is this bringing it down to zero? Is that the equivalent of measuring every particle?
No. So there are two different things. So when I bring it down to zero temperature, that's always the temperature's energy scale versus the relative energy scales in the problem. If I have a very deep potential well, such that the energy cost of taking the electron and moving it outside of that well is huge compared to the energy scale of the temperature that we're looking at, then I can just neglect the idea that it can hop out, because you'll do the experiment. You have to do the experiment more times than you have time in the lifetime of the universe to see it, right?
Yeah.
When it's cold. Of course, if I heat it up, it's free to wiggle around.
One last question on that. You just mentioned at the end of your lecture this question of interaction of quantum objects.
Yeah.
And this is probably out of left field, but in certain quantum mechanical experiments, I understood that you have only self-interference. So an electron going through the two-slit experiment, if you got 100 million of them, each one interferes only with itself. Its waves only interfere with its other waves of that one, and not with any of the others. The same with a photon.
Sure. So that's because in the double-slit experiment for the electron, what I'm doing is I'm shooting one electron at a time. And I shoot it, and I wait for it to hit the detector, and then I shoot the next one. So once it hits the detector,
if I shoot 100 million at once, each one still only, in theory, each one still only interferes with itself.
No, if I shoot two electrons at the same time, they'll interact. Two electrons are charged, so they're forces that act on each other. It's a weaker effect than its self-interference, but it's still an effect that's there.
So it's not true that there's only self-interference of a quantum mechanical object?
Of course not, right? Because you know, for instance, right, so how did they see the Higgs boson at the LHC, right? They had some heavy particle, and what they know happened was that it interacted with some virtual Higgs particles, and then those decayed to photons. So it's clear that that heavy quark jet didn't just self-interact with itself. It also interacted with other virtual particles, including the Higgs boson, which then also interacted with photons so that that Higgs-anti-Higgs pair could annihilate and become the photons. Quantum mechanical particles are always interacting with other quantum mechanical particles. It's just a question of the strength of that interaction. And so there are, of course, limits in which you can neglect it. Now there's a subtlety, which is photons. If I don't have any charged matter, photons are very special in that they really don't self-interact. So if I just have photons and I have no other charged particles that I'm worried about, then I can shoot more than one photon at once, and photons don't interact with each other unless you have other charged particles around for them to kind of scatter off of. So for photons, it's a very special case. But electrons do, of course, self-interact because they're charged. Yes?
Can you go over that term degeneracy one more time? I didn't kind of quite get that.
Oh, sure, yeah. So degeneracy is just the idea that, okay, so here's a picture of, this is kind of a on its side histogram plot of the number of states at each energy. And it's clear that, okay, so as I go up, no states, no states, no states, and a whole bunch of states, all at roughly the same energy. So that's what I'd call a degeneracy. They're all really kind of sitting, their energy is the same, even though the states are different. Of course, these are fermionic states because they're electrons. So if there was really only one state here, it would just be one tiny bump, because I can't put more than one electron in there. But if I have lots of different states with nearly the same energy, I can think of that as a degeneracy because I can put a lot of electrons in all at the same energy. That's what degeneracy means. Yeah, sorry if I...
Yes, okay, so the magnetic field is going up, and you're saying, okay...
No, sorry, so this is a plot of energy, and then this axis, this is just labeling, this is at no magnetic field, this is an applied magnetic field with no scattering, this is an applied magnetic field with scattering. But this direction here is just the number of states. It's a histogram, right? So that's why here I get a bunch of localized states, and then more extended states, and then localized states. Localized, extended, localized.
So in a way, even though one is higher than the other, in each one of those bars, the energy is the same.
In here, the energy is exactly the same. Here, since this is an increasing energy, I find that this kind of exact degeneracy, where every state here is really mathematically exactly the same energy as every other state, when I include the dirt in the sample, I see that it gets kind of spread out, which makes sense, right? If all of these things are really exactly the same energy, you know you must have made some sort of unfair approximation, because it's kind of a rule of thumb in physics that you never get exact degeneracies unless there is a exact symmetry of the system guaranteeing that for you. So for instance, if I have an electron and I don't, say, apply electric or magnetic fields, then I know that the spin up state and the spin down state have exactly the same energy because there is a symmetry reflecting between the two. But if I apply electric and magnetic fields, reflection and time reversal aren't good symmetries anymore. So up spin and down spin don't have to have the same energy. Any other questions? Thank you.